2.17. The spool. A spool consists of an axle of radius lowercase r and an outside circle of radius uppercase R which rolls on the ground. A thread is wrapped around the axle and is pulled with a tension T at an angle theta with the horizontal. See figure 2.24. Given uppercase R and lowercase r, what should theta be so that the spool doesn't move? Assume that the friction between the spool and the ground is large enough so that the spool doesn't slip. Given uppercase R, lowercase r, and the coefficient of friction mu between the spool and the ground, what is the largest value of T for which the spool remains at rest? Given uppercase R and mu, what should lowercase r be so that you can make the spool slip from the static position with as small of a T as possible? That is, what should lowercase r be so that the upper bound on T in part B is as small as possible? What is the resulting value of T? So now let's move on to part A, and the first part is about statics. This means that the net tau is equal to 0, the net fx is equal to 0, and the net fy is equal to 0. Let's first start with a force diagram, and we're going to start with the tension. We have in the x direction t cosine theta, and in the y direction t sine theta. We also have a vertical downwards weight force that's coming from the center of the spool. Because the tension is going to be pulling it right, we have friction that will oppose the motion, so this is going to be to the left. We also have a normal force, which is going to be shown later. So we're going to start with the net fx is equal to 0. We have two forces that have to balance each other. T cosine theta minus f is equal to 0, and then we have t cosine theta is equal to f. So now we're going to look at the net tau of the system, which has to equal 0, and we're going to start from a clean slate. We're going to use that the axis of rotation is in the center so that we'll only have two forces, the tension and the friction, and both of them have a 90-degree angle. Now we can see that they are both in opposite directions, so they must cancel each other out. They also have different radiuses, which gives us this equation. We will now substitute our past relationship that we got from the net fx into our friction. So now we have t times lowercase r is equal to t cosine theta times uppercase r. Now we get the relationship for cosine theta, and because part A asks us to solve for theta, we get theta is arc cosine of lowercase r over uppercase r. So a big ask and a concern might be, why didn't you use mu fn? Of course, we can find n because of the net fy. However, mu is unknown in this part, so it wouldn't make sense because then you just give yourself another unknown. Now, for part B, what we're trying to do is find the maximum tension, and for that, we need the relationship with tension and everything else. This is a good time to use what we were talking about later on. So now we're going to use that the net fy has to be equal to 0. Here we have three forces instead. We have n, mg, and t sine theta, and we get this. We can now use our previously found relationship t cosine theta is equal to f. We also know that f is equal or less than mu fn. And now we have a relationship between these two things. It is fine to use mu fn now because we do have the variable mu. Now we have t cosine theta is less than or equal to mu times mg minus t sine theta. Now all we have to do is solve this for t. Now that we found t, I'm going to take the extra step and use part A to change what is cosine theta and sine theta in terms of lowercase r and uppercase r. So now that we know that t is less than or equal to this, to find the maximum, then this will just have to be when t is equal to this. So now we're going to move on to part C, where we're trying to find the r that minimizes our t max. This is possible, as we're showing in part B, because t depends on theta, which depends on r. Now we have t equals mu mg over cosine theta plus mu sine theta. Just to visualize, I'm going to show you this base function as a graph. We cannot have negative values for our system, so that's why we can cross out all the things below the x-axis, and this shows us that there are minimums which we need to find in the tension graph. So now, to do that, we're going to take the derivative of this tension function, and we get mu mg sine theta minus mu cosine theta over mu sine theta plus cosine theta squared. And we need to set this equal to 0. It only matters that the numerator is 0, and it just matters that the denominator is not 0 at this time. So here we get sine theta is equal to mu cosine theta, so we have tan theta is equal to mu is when this is minimized. Now we can look back at our triangle and realize that tan theta is equal to mu is also equal to the square root of r squared minus r squared over r. Here we can now just solve for r. And we get what r is equal to. That minimizes the tension.